All right, so an important topic on nuclear chemistry is half-life. So think back, we've already talked about this, so review your kinetics. I know it's been a while, but hopefully you didn't forget everything. And then remember, the half-life is the time it takes until the concentration is half of what it originally was. And all nuclear reactions follow a first-order rate law. And so remember, think back what that means. It means rate equals K times the concentration of whatever you're looking at. And then the sum of these exponents has to just be 1 in order to be first order. So it's only dependent on one thing and one thing only. And so if we solve for the T1/2 of this, again, review your stuff, T1/2, you're going to get to this 0.693 over K. And so the main thing for this half-life is that it's independent of concentration. And so what that means is that this half-life is constant. Since it's independent of concentration, the first half-life is going to be the same length as the second half-life, the third half-life, the fourth half-life, and so on and so forth. And so it's very useful to date things, to figure out how old something is. So here's just kind of a diagram of that. So here we have cobalt-60 decaying, and so you can see each half-life is 5.27 years, right? So the first half-life takes the same amount of time as the second half-life, as the third half-life, fourth half-life, fifth half-life, and so on and so forth. Now, to kind of solve problems and to do some calculations, what we really want to look at is the integrated half-life. And so remember, the integrated half-life is what's going to allow us to relate time and concentration. So remember, T1/2 here is 0.693 over K. And then when we integrate it, we can move some stuff around. We get the natural log of A at time T over A at the original is equal to negative KT. Again, this A at time T is the concentration at time T. So that's whatever time you're interested in after 20 minutes, 30 minutes, whatever. This one on the bottom here is the original concentration. K is the rate constant, and it depends on the nucleus. And then T is your time, right? How long did it take to go from this concentration to that concentration? And so there's a whole bunch of different nuclei you can use for different things. So you can use stuff for dating to see how old stuff is. You can date the Earth, date all kinds of different things. There's also a lot of medical uses. So there's an example of some radioactive isotopes that are used in medical uses, and you can tell even these have quite a different decay half-life, right? Some are very short, some are very long, and you can go further than that. Those are just the ones for the medical uses. One of the most popular examples of this dating is carbon dating, right? Figuring out how old some dead animal, dinosaur, whatever it is. So let's take a look at that. So from outer space, we are constantly bombarded with neutrons. These neutrons are absorbed by nitrogen atoms in the atmosphere, which then decay into slight traces of carbon-14. Carbon-14 made in atmosphere. This carbon-14 is then absorbed by plants to make matter, right, through photosynthesis. And so it gets absorbed by living things, and it's constantly replenished if the animal or plant is alive. They're constantly renewing their concentration of carbon-14, And so the overall concentration of carbon-14 in a live animal is constant because it's being constantly replenished. So we'll say living, and then C14 is replenished. And then when it dies, right, when it dies, it's no longer being replenished. And so when it dies, the decay starts. And based on how much carbon-14 is left in that dead carcass, you can tell how old it is. So we'll take a look at that, an example of that coming up.